So, we were about to prove that the maximal ideals. So, that is we are looking at a commutative unital Banach algebra and maximal ideals and the collection of multiplicative linear functionals, right. They are in 1:1 correspondence, in the sense that if I take a multiplicative linear functional phi and look at kernel of phi, that is a maximal ideal, and if I take a maximal ideal, there is a multiplicative linear functional whose kernel is that precisely that maximal ideal, okay. And this map is 1:1. Okay. So, let us complete the proof of that. So, remember this is the theorem we are looking at. We proved one way, if phi is in sigma a. So, that is phi is a multiplicative linear functional, then kernel of phi is maximal, and if kernel of phi is equal, phi 1 equal to kernel of phi 2. So, if once we have this equality, then phi 1 is equal to phi 2, right. So, we have a 1:1 map. We need to show that if I start with a maximal ideal M contained in A, then we need to construct a phi in sigma A, that means multiplicative linear functional, such that kernel of phi is equal to that maximal ideal space M. Okay. Okay. So, let us prove that. Okay. Now, note that M is closed. So, M is closed. Note that M is closed. So, as a subspace is closed, okay. Hence, one can look at A quotiented with M, right. So, M is a closed subspace of A, you can do the quotienting and it becomes a Banach space, right. So, we look at the projection map. So, let pi from A to A by M be the natural map, right, be the map. So, A going to A plus M, right. So, that takes you to the quotient space. Now, since M is closed, we know that A quotiented with M is a Banach space, right, is a Banach space with the norm. So, I take a element A plus M in A quotiented with M, and what is the norm of this? So, this is infimum of norm of A plus M, where M runs over script M, right. So, that is called the quotient norm, right, which is what makes A by M into a Banach space, and we will see that it also makes it into a Banach algebra. So, on A by M there is a natural multiplication, that is easy to see, right. So, define A plus M into B plus M. So, that is the multiplication which I am defining on the quotient space. So, I want to say it is a Banach algebra. So, this is simply A B plus M. Okay. Of course, if I define something like this, you need to check that this is well defined. So, check that this is well defined. What does that mean? That is, if A plus M equal to, let us say, A prime plus M, right, that means A minus A prime is in M, and similarly B plus M is equal to B prime plus M, then A B plus M is equal to A prime B prime plus M, right. Otherwise, you will get a different entity, and then there will not be the definition of multiplication will not make sense, right. So, but this is easy to check, because if A and A prime differ by an element in M and B and B prime differ by another element in M, then you can see that this is same, okay. And you also prove that this is well defined. So, you have to use the fact that M is an ideal, okay. So, use the fact that M is an ideal. right. Any term like A times m will be in M. Okay. Okay. Now, we want to say this is a Banach algebra. Okay. Now, check that this norm makes the quotient space, that is A by m, into a Banach algebra. It is a Banach space, we already know. I am saying with this norm and the multiplication, we have actually a Banach algebra. Okay. So, what do you need to check? Well, I will leave this to you. This is actually straightforward. So, what do you need to check? A plus m, b plus m norm is less than or equal to norm of A plus m into norm of B plus m, right. So, you can take elements in M and look at A plus m into B plus m prime and use the Banach algebra property for A and then argue that this is true. Okay. Now, next claim is that, so we claim that this new Banach algebra A divided by m has no proper ideals. Okay. Well, this is because we have quotiented out the maximal ideal m, right. So, there should not be anything remaining, but let us argue. So, why is that? Suppose I contained in A quotiented with m. So, it is a subspace of A quotiented with m and it is a subalgebra and an ideal. Okay. So, I is an ideal, is a proper ideal. Okay. Now, recall the map pi. So, pi from A to A quotiented with m, right. So, we have this map. Now, if I look at, so consider pi inverse of I. Okay. So, I am looking at all those points. So, what is this? This is all those points A in script A such that pi of A is in I, right. Now, it is easy to see that this is an ideal. So, easy to see that pi inverse of I. So, you can check this straightforward is an ideal and m is contained in pi inverse I, alright. So, this will tell me that because m is maximal, but m is maximal implies. So, m is maximal would imply that m is equal to pi inverse I or pi inverse I is the whole space, right. These are the only possibilities, that is m is equal to pi inverse I or pi inverse I is the whole thing, right. In other words, so this would imply I equal to m or I equal to A by m, right. These are the only, right. So, there are no ideals. So, I equal to m meaning m is the 0 element, right, 0 element in the quotient space. So, I is 0 or the whole thing, right. So, there are no proper ideals. Okay. So, now if I take, so A by m is a Banach algebra with no proper ideals. Okay. Hence, any non-zero x in A by m. Okay. So, when I write x, it is actually an element in the quotient space. Okay. Just to simplify the notation, I write x. Any non-zero x in A by m is invertible. Okay. If not, well, what will happen? If not, you can look at the ideal generated by x, that will have to be proper, right. If it has identity, it is the whole space, that means it is x is invertible, right. So, if x is not invertible, the ideal generated by x in a Banach algebra is proper, right. If not, the ideal generated by x in A by m is proper and non trivial, right, because x is there. So, that is a contradiction because we have just proved that there are no proper ideals. Okay. Consequently, well, what did we just say? We said that any non-zero element in a Banach algebra with identity is invertible. Then by Gelfand-Mazur theorem tells me that this is the complex plane, right. Consequently, by Gelfand-Mazur, A by M is the complex plane, right. So, in other words, A by M would be just lambda times let us say identity. I will put a bracket so that it is the equivalence class, right, with lambda in C, right. So, that is how A by M would look like by Gelfand-Mazur. So, now so let us call that isomorphism phi. So, let phi stand for A by M to C, the isomorphism, that is lambda e going to lambda, right, that is simple. So, we have pi from A to A by M to C, right, this is phi. Okay. So, define psi to be equal to phi composed with pi. So, this is from A to C. Okay. Then psi is a multiplicative linear function, and that is very easy to see because these are all continuous first of all. So, composition is continuous, pi is multiplicative, right, A going to A by M, that is by definition it is multiplicative, right, because A going to A plus M is the map. So, A B going to A B plus M is the product of A plus M and B plus M, that is how the multiplication is defined. So, it is obviously a multiplicative map, and the lambda e going to lambda, that is phi, that is also multiplicative. So, composition is multiplicative and it is a multiplicative linear function. Okay. So, that is a right with important part is kernel of psi equal to M, right. So, that tells me that all maximal ideals are kernels of multiplicative linear functionals, and these kernels uniquely determine the multiplicative linear function. Sigma A is called the spectrum of A, is the space of multiplicative linear functionals or the space of maximal ideals. Okay, depending on the book you look at, these two terms will be interchanged because there is a 1:1 correspondence now between multiplicative linear functionals and maximal ideals. So, let us look at example. So, look at C of x. So, that is my Banach algebra where x is compact T2. Okay. Let phi from Cx to C be a multiplicative linear functional. Okay. So, we have seen, so maybe I should repeat that, we have seen some examples of multiplicative linear functions, right. So, if I fix x naught in x and define f going to f of x naught, right. So, this is from C of x to C, then this is multiplicative, right. So, then so we call this phi sub x naught, right. Then phi sub x naught belongs to sigma of C of x, right. So, it is one of the multiplicative linear functional. We want to say that these are all. Okay. So, let us see if I will prove this. Yeah. Okay. So, we will prove this. Okay. So, claim. Okay. So, kernel of phi sub x naught equal to all those f in C of x, right, all the continuous function. The phi sub x naught is simply evaluation at x naught, right. So, this is simply f of x naught equal to 0, right. The kernel is simply, so you look at all those functions vanishing at one point, right, one fixed point, then you get the kernel of that particular multiplicative linear function, and so this is a maximal ideal. Okay, maximal ideal in the Banach algebra, right. What we want to say is these are all, that means all maximal ideals are precisely of this form, that means there is one point and you look at all continuous functions vanishing at that point. Okay. That will follow once we show that all multiplicative linear functionals are precisely pointwise evaluations, right. So, if I take a multiplicative linear functional on C of x, then there is some point x naught such that the multiplicative linear functional is simply evaluating the function at that point x naught, right. So, we have to prove that. So, once we prove that, all maximal ideals are characterized. Okay. So, let us do that. Okay. So, we will call this m sub x naught. Okay. So, clearly it is a maximal ideal. Now, suppose m is a maximal ideal, Okay. So, remember the pointwise product is the product in the Banach algebra, ideal meaning with respect to that product, right. So, you have a subalgebra such that you multiply with any function in C of x, you still land there. Okay. So, we want to show that. So, we want to show that there exists x naught in capital X, in the space capital X, such that m is equal to m x naught, right. So, all the functions will vanish at a point, right, that is what we want to show. Okay. So, let us try to prove this. Suppose not, suppose there exists no x naught in x such that f of x naught equal to 0 for every f in M. Okay. So, M is a fixed maximal ideal and I want to show that M is actually equal to m sub x naught, right. So, I want to find a point where all these functions are vanishing, right, that particular point x naught on which all these functions vanish. Suppose not, that means I am assuming there is no x naught such that that is happening. Okay. So, whatever point I take, so this is my x, whatever point I take, there is a function in the maximal ideal which does not vanish there, right. Okay. So, then for every x in x, so let us say this is x, right, that is a point there, there exists a function, there exists f in C of x. Of course, if I change the point to some other point, the function will change, right. So, let me put f sub x. So, f sub x is a function in C of x. So, it is a continuous function such that at that particular point x, f sub x is non-zero, right. So, for each point, so if I change the point y, I will have an f sub y and so on, right. So, at each point I have a continuous function which is non-zero, but not in C of x, right, that is not what we want something in M, right, because we are assuming that there is no x naught on which all of them vanish, right. Okay. So, there exists f sub x in M such that f sub x at x is not 0. Okay. Now, it is a continuous function. So, if it is not 0 at some point, there is a neighborhood around it where it is not 0. Okay. So, let us call that neighborhood u sub x, right. So, there exists a neighborhood u sub x of x such that f x at t is not 0 for t in u sub x, right. So, in this neighborhood u sub x, my function is non-zero because at x it is not 0. So, there is a small number. Okay. Now, you see I am doing this for all points, right, whatever point I take, there is a neighborhood and a function, that function comes from M, right, the maximal ideal where it is non-zero. Okay. So, now if I look at all these neighborhoods x in x, right, for each point I have this u sub x, right. So, it will cover x, right. So, this is an open cover for open cover for x. Remember x is compact Hausdorff, right. Since x is compact and I have a open cover, there exists a finite cover, right. Hence, there exists x 1. So, the finite cover will be let us say u x 1, u x 2 etcetera u x n, right. So, x 1, x 2 etcetera x capital N in capital X such that the corresponding neighborhoods cover x, right, such that x is equal to union u sub x j equal to 1 to n, right. So, because x is compact you can do this. Now, what was the property of these neighborhoods? The corresponding function, right, that will be non-zero there. Okay. So, we use this is an open cover. So, define g. So, g is going to be a new function which is going to be defined using these f sub x j's. So, remember each neighborhood gives me a one function which is non-zero there, right. So, f x j, okay. Then I multiply it with f x j bar and I add some j equal to 1 to n. Okay. So, this is nothing but summation j equal to 1 to n mod f x j square, right. So, g at y will be summation mod f x j at y square summation j equal to 1 to n, right. Well, what can you say about this function? Where are these guys? These are in the maximal ideal M, right, and these are in C of x, right. It is a continuous function, right. F x j is a continuous function, its bar is a continuous. So, when I multiply, because M is an ideal, the product will be in M. When I add, they will still be in M, right. M is going to M is an ideal. So, G will be in M. Okay. So, from the fact that there is no x naught on which all functions vanish, we have constructed some function g using compactness of capital X, right, the space X. What is the property of g? If I take any point in the space, right, so that is going to be in some neighborhood, right, u sub y, right. Well, not u sub y, it will be in one of these neighborhoods, right. So, then there exists j naught such that y belongs to u x j naught, right. For some let us say it is an x 1, right, instead of x j naught, it will be there. Okay. So, that implies that g y, so this function we have constructed at y will be, well, this is equal to summation j equal to 1 to n mod f x j at y square. Okay. But one of them is where that particular function is non-zero, right, because y is in u x j naught and on x j naught. So, this is greater than or equal to mod f x j naught at y square, and that is strictly positive, right, because that particular function f x j naught is strictly positive in the neighborhood u x j naught, right. So, what did we do? We constructed a function in M which is never 0, right, it is strictly positive. So, 1 by g, since g is continuous and strictly positive, 1 by g is also there, right. So, 1 by g is in, okay, because g is strictly positive, but then g is invertible, right, hence g is invertible, hence g is invertible. And so, script m, the maximal ideal will have to be the whole space, right. Okay. So, that proves that. So, this is a contradiction, right, because it is a maximal ideal. So, it is proper. So, it cannot be equal to C of x, which means that m phi. So, the assumption was that, so that is m is equal to m x naught for some x naught. For some x naught in x, right. So, all functions, so the maximal ideals are precisely those functions vanishing at some point, right, which is same as saying all multiplicative linear functionals are point evaluation at certain point, right. So, if I take a multiplicative linear functional on C of x, then it is just f going to f of x naught for some point x naught. Okay. Okay. So, that takes care of C of x. We will also look at L1 of R and L1 of Z later. Okay. We will look at what are multiplicative linear functionals there, things like that. Okay. But for the time being, let us move on. So, Gelfand transform. So, now we study Gelfand transform on A. Okay. So, let A be a commutative unital Banach algebra as usual. Okay. For x in A, define. So, we looked at various objects associated with A, right. So, it is good to remember that. So, we had the spectrum of A, right. This is the maximal ideal space of A or all multiplicative linear functionals on A, right. Now, this was sitting inside the unit ball in the dual of A, right. So, A1 star, and it turned out to be, because it is closed in the weak star topology, this was a compact T2 space. Okay. Now, we are going to define what is known as Gelfand transform. So, define x hat. Okay. So, that is a notation. Okay. So, x hat is going to be a function from sigma A. So, what is sigma A? Sigma A is a compact Hausdorff space, right. It is sitting inside A1 star in the unit ball of the dual of A, but it is a compact Hausdorff space, and I am defining a function on this compact Hausdorff space to see by, well, the definition is very easy, x hat at. So, sigma A is a collection of all multiplicative linear functionals, right. So, I can define x hat at phi. What is phi? Phi is a multiplicative linear function. Well, how is it defined? This is phi of x. Okay. So, let me repeat, x hat, this is called the Gelfand transform. So, the map x going to x hat is called the Gelfand transform. So, let me say let me write down that the map x going to x hat is called the Gelfand transform, is called the Gelfand transform. Well, where is x hat? X hat is a function defined on sigma of A. Sigma of A is a collection of all multiplicative linear functionals, and that is a compact Hausdorff space. Okay. And it is a x hat is a function defined on that compact Hausdorff space. Now, notice that it is not just a function, right, it is continuous. So, note that x hat is a continuous function, on this compact Hausdorff space sigma I. Well, why is that? If I take, how do I prove something is continuous? Well, you can take a sequence of net, a sequence or a net in sigma A. So, let phi alpha be in sigma A and phi alpha converges to phi, right. So, everything is happening in my compact Hausdorff space, right. So, what happens to x hat of phi alpha? Well, this is phi alpha of x, right, that is the definition. But what is phi alpha converging to phi? What is the meaning of that? Phi alpha converges to phi in sigma of A. Remember, the topology is the weak star topology, which is pointwise topology, right. So, this is equivalent to phi alpha of y converging to phi of y for every y in A, right, that is the topology. Okay. So, phi alpha of x, so this will converge to phi of x, but this is simply x hat at phi, right. So, I started with a net phi alpha such that phi alpha converges to phi. I proved that x hat at phi alpha converges to x hat at phi, implies x hat is continuous, Okay. So, the map x going to x hat Okay. So, hence the Gelfand transform x going to x hat is a map from script A into continuous functions on this Hausdorff space sigma I, right. So, that is the Gelfand transform. Okay. So, it is good to think about it and understand a little this very clearly. So, starting with the commutative Banach algebra A with identity and so on, we looked at maximal linear function maximal ideal space, that is same as continuous multiplicative linear functionals on A, and we defined this Gelfand transform. Well, we defined the Gelfand transform to be a function on the space of multiplicative linear functionals. The multiplicative linear functionals is a compact Hausdorff space with respect to the weak star topology, and if I take a point x in A, I am able to define x hat as a continuous function on this compact Hausdorff space sigma A, right. So, I have this map x going to x hat. Now, we will study the properties of these this Gelfand transform. So, what you need to understand is the abstract Banach algebra we started with, which is script A, each point there is now viewed as a continuous function on a compact Hausdorff space, right. So, if you remember all the examples we looked at was the continuous functions on compact Hausdorff space, right. That was the easy example we kept looking at, and we are trying to embed our Banach algebra into a concrete algebra like C of x, where x is compact T2. Okay. So, we will stop here for the time being, and we will continue with the study of Gelfand transform in the next lecture.